This is the Apollo 13. What you maybe don't know is that it got a brother or a sister, who knows, that was actually a digital twin of himself. Andrea today is going to explain us what is a digital twin engine and why it's so important and why interTwin put a lot of effort to make it work. So please, Andrea, if you don't mind, present yourself and this project.
Hello everyone, so I'm Andrea Manzi and I'm working at the AGI Foundation in Amsterdam. We are the coordinator of this project. Actually, I'm the technical coordinator. We also do project management. I've been working in this company for 5 years, and previously I have experience also in other scientific domain. Like I've been working at CERN for 10 years.
So sorry to interrupt. What's the core business of AGI?
Yes, we are basically coordinating distributed infrastructure in Europe. So we deliver like services for advanced computing, ranging from data analysis, cloud computing, HTC, and then now we are expanding also to HPC computing, which is also related to what we are doing in interTwin. And nothing. We are 15 years that this is not a private company, it's a non-profit, has been created, and I'm there since 2020. So the project started in 2022, so in September 2022. Maybe we can start discussing and introducing the digital twin.
Yeah, you're doing the questions. No, okay, yeah. Considering exactly that we are converging toward an end of the project, and it would be nice to, creating kind of a timeline where we started, why we started, and how this is going, the project is going, and exactly why digital twins are important in it.
So when we started the proposal, so this was back in 2020, we basically we wanted to have a solution, to build a solution which could be reused in many domains. So not only targeting a specific scientific domain for digital twins, but basically having a generic solution that could be reused to build digital twins application, in our case, in scientific domains which range from environment, physics, astrophysics, so different type of sciences.
We have, by the way, for each one of these cases, we will have dedicated.
Yeah, of course, we are not going to discuss too much in details because we will have dedicated.
Just a tiny bit,
of course. And this basically the concept of digital twins, in particular for scientific digital twins, started like around the 70s. This basically during the time there was one of the mission of the Apollo 13 that was launched to the moon, and during the time there was an issue with one of the oxygen tank that exploded during the trip to the moon, let's say, and NASA managed to run multiple simulation, taking into account, the physical model that they have of this Apollo 13, improving, the let's say the physical model with digital components that were developed during this period. And basically they built digital twins out of the Apollo 13 mission. So they ran simulation, feeding this with the real data that were coming also from the accident, and they could manage to understand, what were the issues, and basically instruct the Apollo 13 crowd in order to come back easily without problem after the accident. So basically, we can say that this was the first example of digital twin for, and of course, it was a successful example because, of course, this saved lives of the astronauts that were on the Apollo 13.
And we went a long way since then.
Of course, now that there are different definitions, of course, of digital twins, but in particular for this project, we've adopted a definition that digital twin is a virtual representation of physical object, system, or process, which is created and sustained with the information that are coming from one of many data sources, but also from models, which can be physical model, AI models, And then they consider, of course, both historical observation, but also real-time data. So this is the characteristic that we see, say the definition that we have used in the project so far. We have different type of digital twins. Of course, since the beginning, the first adopters have been the industry, so they in the manufacturing, so they have adopted digital twins for the lifecycle management products, and this has been used mainly for interventions, so for adaptive design, for R&D, construction and maintenance, to reduce the maintenance support for the products that they were building. So with a time span of seconds to 5 years of those digital twins. But then, of course, we have seen these terms used also in the context of smart cities or airports or ports. So when basically digital twins out of entire cities of buildings, let's say, have been used quite a lot. But then, of course, recently, in particular, also with the funding also coming from the European Commission, we have seen also the term digital twins being used mainly for also for the environment domain, where basically we could use digital twins in order to help with the decision support and the risk management. So helping like policymakers understanding, the impact of climate change, and then of course, take decision based on
all right. So
what's
essentially the fil rouge probably is making experiments with the reality, right?
Yeah.
So you want the capability not to experience explosion of a tank real life, but you want to do some experiment with reality. Yeah. Anything else?
Yeah, indeed. What as I was mentioning, so this project, but also a lot of funding has been, let's say, pushed also by the European Commission in order to build, in particular, on the environment domain. So we have a big initiative in Europe which is called Destination Earth, which aiming at having an operational system of a digital replica of the Earth. So creating like basically updating the digital twins of the Earth, in particular, starting now with the digital twins which are creating and alerting the case of extreme events.
Okay.
This is the most, let's say, important that is operational at the moment, but they will be extended with others. And then we have also a big initiative which is about the digital twin of the ocean, which is basically twin similar of Destination Earth, but for the marine and the ocean ecosystem. And then we have projects like interTwin, which they want to have, as I mentioned before, to be interdisciplinary, so to have a way to build digital twins which are can be in the scientific domain, but with in different fields. In particular, this, if you want, I can describe a little bit what is the status of the project, given that we are at the end.
yeah. I'm interested in also not only the final result, let's say, but how this complexity, because I suppose we know because we were part of the same adventure, if you want. There are a lot of data, or if not a lot, complex data. There is the need for computational power, and then there are final user, the developer of these models that should access them in a coherent way. And every time you are in this situation, the complexity is also from the part where the people should communicate. So also how the working group have worked together for a solution that can be common for digital twins. So I see all these moving parts. So how was the experience on coordinating this from your point of view?
Indeed. Now, for instance, our project is, as you know, is delivering a digital twin engine. So this is the software infrastructure which support the design and the build and also the operation of digital twins. And of course, what does it mean is that the software infrastructure is helping the orchestration of core flows, the data flows that are needed, to build models, and of course, update the models when running, of course, which means data fusion, data simulation, and in particular, in the environment domain. And as I mentioned before, we wanted to have a solution which was used by different domains. So this is why we have different pilots or use cases in particular two macro domains, which is the domain of the physics, which includes, of course, also astrophysics, particle physics, lattice QCD, and environmental science, but including environmentals in the so climate and also adaptation. And then basically we have been working with different type of stakeholders in the project. So meaning that we have from one side the providers of resources, so the ones that they give access to HPC, HTC, and cloud resources, because we have seen that, of course, depending on the type of workflow that is needed by the digital twins, we could use different type of paradigms. You use cloud because we want to host particular type of model inference. You need HPC because you need access to multiple GPUs in parallel in order to train the different models. And then, of course,
and this is a pattern also that it's becoming more common as the machine learning, AI stuff is coming through. So yeah, I suppose it started from this, but it
applies
more,
now.
Applies
to different so domain of digital twins, because now we are doing, but of course this is quite common now in different for different solutions. And then indeed, of course, we the consortium of the project includes as well, of course, the technology providers, developers, because we have to build the software, and then of course all the communities that are providing use cases and pilots. They're also important because they participated, of course, in the co-design phase of these components and the platform. And of course, when the first prototype, the first software was developed, they have helped with the validation by integrating the components developed by the DTE in order to build their use cases. So the use cases quite quickly, we have, as I said before, we have two categories. So the one from climate research and environment. So we have extreme events, digital twins, tropical cyclones, flood, and wildfire, but also draft, in particular the draft of the Alps, an early warning digital twins for that, and then a flood impact modeling. We have different institutions that are collaborating and building, finalizing, of course, because we are on the project, finalizing those digital twin applications. So CMCC, University of Trento, CNRS, EURAC Research, Deltares, which is a private company, Technical University of Wien. So all these, they provide the use cases in this domain. And then on the other side, we have the physics use cases, in particular, the ones that are dealing with the digital twins for the high energy physics detector, the one from CERN. So CERN is part of the project that is working in this particular use case, but also the virtual gravitational wave interferometer digital twins, which is basically coordinated by NFN. And also the two related to radio astronomy, radio simulation, which is from the University of Heidelberg and Max Planck Society, and the lattice QCD, which is the one that is coordinated by CSIC and ETHZ.
Yeah, we'll have basically a chat with all of
that.
So,
of course, you will see later the details of those.
Yeah, I suppose also it's a challenge by itself, making all these different worlds talk to each other. So
yeah, it's
or at least using
the problem, of course, is that those domains, apart from the different problems that they have to they've brought to the table, they have different type of data, of course, because this is the main input for building digital twins. And,
there are data in data. Of course, I suppose it's not in the same format would be too easy.
Of course, they're different format. They have also the access to data is different, because some of those, in order to build digital twins, we need to process historical data that are coming, for instance, from archives, and so to access them, you need tapes access. So we have also a variety of data access that we need to support, and as well but of course the main thing that we wanted to have in the project is to understand commonalities between the different use cases, and then brought have a solutions that could be used by both, let's say, in particular for the access to the infrastructure, but also for the build of the workflows and for the validation of for the AI part and validation of the models. Of course, we know that not everything can be generalized. So indeed, the project is divided in particular in three main areas. So um, we have a part related to the infrastructure service. So basically all the services that are dealing with the access to the resources, AI, orchestrating the deployment over the different type of resources, federating the access to the compute and of the data management. Then we have a set of core functionalities, which are basically shared between all the different use cases. In particular, as I mentioned before, we're talking about workflow composition, AI and machine learning, big data analytics, and data fusion, but also the part related to real-time access, data acquisition. And then, since we know that we have different use cases, we have part of the project which is dealing with the development of thematic functionalities, which are tailored to the needs of the different digital twins applications. So we have a set of thematic modules which either are complementing what is developed in the core part, or they are basically dedicated models which are used by the digital twin applications. And I didn't mention, of course, that our main stakeholders in the projects are the developers of digital twins. So we are building this platform for developers in order to provide both the thematic modules that are needed and need to be integrated with the core, and then of course to provide we call DT application because they are the let's say the user facing part of the digital twins.
Right. There are user,
Yeah.
and there are user of the digital twin engine
Yep.
that are the actual researcher or figures that are
Yeah,
doing the development.
And then of course they have the users, the end users in our case, who are the scientists, the policymakers. They can access what has been developed as a digital twin, of course, and then they use it the prototypes that have been made available. And then, of course, given that we have almost at the end of the project, our main focus and main results has been, first of all, to deliver the software packages that compose the components that are compose the digital twin engine. So we have a set of components which are, of course, open source, so everything is available on GitHub. We have a community on GitHub which contains all the software that has been developed from scratch. Of course, we are not developing everything. We are also extending existing solutions as usual. And
rightfully,
because and then the different institutions that are developed the different components are committed to continue the supporting of those as building a kind of open source community around it. In particular, as you know, as you've been the main developer of that, we have one of those components has been included as CNCF sandbox project since March this year, which is Interlink, which is our component for the computing federation. And then, of course, this will give for visibility and possibility, of course, to more contribution from external to this project, of course.
Yeah, and it's one of the aspects that it's transversal to digital twins. I mean, it's not only a digital twin needs; it can be any kind of need for this kind of approach. So yeah,
and of course, you know that you have seen a lot of interest around this component, and in different situation, different projects or needs that are
even projects
not dealing with digital twins. So maybe what I can say is that the different components that are part of the layers, which are the infrastructure and the core, basically they allow, as I mentioned before, like access to via federated login to different infrastructure components. So the hardware resources like HTC, HPC, cloud, and data repositories. So we have developed components in this area or used components that coming from AGI in this case. We have components for the orchestration of resources. These components um, have been extended also to use AI in order to take the best decision when deploying an application on top of clouds. For the federated compute, our main development has been Interlink, which is the software which basically allows to connect different type of computing backends following the Kubernetes API. So this is basically our main entry point. And then we have the level of infrastructure. We have a layer of federated data management. So we would like to connect all the different type of storages, regardless if they are HPC storages, they are coming from cloud S3 in a, let's say, uniform way, so that the upper layer or directly the digital twin application can access it transparently, and then they can also use data locality. So basically, you can decide to have like particular data sets local to HPC because you need it for the training, or you need it for inference, so it will be accessed by the cloud.
Yeah, I like this slide that we are sharing, that where you have a stack of solution, of course, because you have to have control on who is using your platform, how you bring up services for this platform, how you exploit other resources, and then of course the fundamental part is how you manage your data and you move data around. So yeah, this factorization I think is very nice. And from the perspective of the user, there is also the nice point to me that they do not have necessarily to know anything about all this stuff, right?
Of course, this is something that we have developed in a way that the user just have a graphical interface in order to, for instance, deploy the service that they're needing, and then they don't need to know the details either. There is a particular cloud behind, or there is a particular HPC that they need to access. Yeah. So this is quite transparent to the users.
And from the other side, from the provider experience also, it's not seamless to be integrated. But I think we are also experiencing that it's becoming more and more easy to add other providers, right? Because the hardest part was to create the instrumentation to make it possible. But then I see the example of the latest providers that we included. It takes less time than the first one because you have experience, you have tool, you have guidance, and it becoming more and more easy.
Yeah, it's true that, as you mentioned, of course, during the project, we had as member a set of providers, which of course they've been funded in order to give access to resources that have been used by the pilots. But of course, we are seeing more interest from different providers in order to join, for instance, either the Compute Federation or the Data Federation. So we have, let's say, kind of early adopter outside of the projects, which are now, testing an integration with via Interlink, for instance, or, installing storage which is compatible with our data lake in order to make available the data that are there in order to. So this is not only, it's these providers are coming from the project, but we have been seen also external, say, adopters, the adopters of in order to provide the resources and to test the integration that we have done in the project. Of course, as I mentioned before, the other important part of the components that we have developed is the core part. We call it core because it basically on top of these are components on top of the infrastructure which are delivering functionalities common for the digital twin application. Doesn't mean that, of course, all of the digital twin application are using all the services and components that we developed. It's not like a monolithic tool that. So it's a set of tools that, of course, some of the use cases needs. So they are using some others. For instance, we have use cases that doesn't use AI. They're not going to use the AI component, of course, because they use physics modeling. And in particular, we have
that might sound like weird in this period of time, but
okay,
it's
not like
it's totally fine. It's because the hype now is AI is everywhere, but it doesn't have to be like that. So.
Indeed, starting from AI, so of course the list of components is quite long, so maybe we can pick some of those. So we have like developed, in particular CERN was the main developer of this iTwin AI component, which is generic ML and AI training framework, which could be easily set up for training and for the inference over different backends. Can be cloud and also HPC, which integrates also with the famous, let's say, model repositories like MLflow and others. And another components which we would like to highlight, it's a component that has been extended with an extensive component which is the name of Oscar. It's a component for event processing and serverless, which we will have also next in line for the podcast. And basically it's been it's nice because this component has been used for in different domains. So basically it's been used both from the environmental digital twins, but also from the physical digital twins, in order to build workflows which could run either on cloud, but also thanks to interlinked on HPC. And then, of course, what is important, one I think, apart from the, let's say, developments that has been done, is also the testbed that has been set up. So, as I mentioned before, we have enabled the access to different HPCs and clouds. So we have clouds in the project which comes from the GI Federation, in particular the ones that are coming from UDC, GRNet, and UKI. This is an external cloud that also being used. And those clouds host mainly high-level services, which are automatically deployed using infrastructure manager or the AI-based orchestrator. And then from those cloud, we can, thanks to interlink, we can offload part of the computation transparently to HPC systems. When I think computation, we have different type, of course. We can have like interactive computation via Jupyter. So we have like a Jupyter Hub, which is hosted, for instance, one of the clouds. And then the possibility to offload the Jupyter servers in transparently into.
So in this sense, your cloud providers are the entry point for the developers, let's say, and then you offload
some part of the computes. In particular, we need of course, some of the computation can be hosted on cloud directly, but of course, when we need access to GPUs and when we need access to memory virtual machines, for instance, or memory nodes, this is quite convenient to go to where those beasts are, so where they are the HPCs. So I think we are quite proud to have done most of the integration with the HPC Vega in Slovenia, which has been quite basically we have done all the initial integration and currently is the major resource provider for us. But we have been also using a Jülich supercomputer, and recently, we have finalized also integration with PSNC in Poland. And this is from the point of view, of course, of the computing, but from the other side, the test beds that we set up, as I mentioned before, are allowed also the data federation. So basically, all the storages which are already existing on HPCs have been federated, and then we developed also solution in order to connect sort of gateways, the storages where those particular solution available HPC was not possible. And yes, in particular, and then of course we have more sites, as I mentioned before, that were not originally part of the project, but we have using like Sesga. I think you have also podcast with the people from Sesga.
So we can say we did it, right? So we have this testbed. Actual use cases that we are going to interview as well that are demonstrating that this can work for the variety of use cases. So congrats.
And to you, of course.
To us. And all right. So I think it was a very interesting introduction to all the other podcasts that we will see. Thanks for your time. Thanks for the explanation. And I don't know. You have any other consideration of your experience you want to share, or that's all we have?
I mean, I want just to say that, of course, it was a long journey because it's 3 years project, you know, and it's not difficult then to have like distributed, because of course when you work with this kind of European project, you have to take into account that you have 30 plus partners,
Yeah,
you know,
exactly.
with different level of interaction, you know, and so it's not an easy task. But I think that the results that we had, it was quite important, and we demonstrated, of course, that this particular digital twin engine can, of course, now is at the level of prototype, but can measure, you know, into a production ready software stack.
All right, so stay tuned for the next episodes. Thank you all. See you soon.
Thank you.